Yeah. Yeah. Hello, my friends. Today, as you see, just I have written the problem statement on, the flocculation. A very typical example. This example is taken from the book P.V. Rowe and Covernoglass, a very popular book indeed, because it covers that entire more or less this water, wastewater, solid waste, then air pollution. So it is that way environmental engineering in complete sense. Now this problem we will solve based on this discussion in our last lecture, where we discussed the various design parameters and also this considerations also. So keeping these considerations or design criteria or parameters in mind also, which actually I told you earlier that these all are given, actually the design parameters last time what we discussed, that is in CPHEEO Manual. So as I have told you earlier, that let me follow the CPHEEO Manual because this should be uniform. And in the book, unlike in the book, actually what happens from book to book it may vary, and it varies in fact. So that is why we will take the CPHEEO Manual, and we can legally, where legal implications or litigations that is there, then you can quote also, and it is accessible. The most importantly, this is accessible to all of you. You can download that, as I have told you. So this is a short design problem. Short, I have not written, but here it will be a short example, because the elaborate examples that needs, a very thorough every details of the drawing which are beyond the scope, because it is an undergraduate level. In postgraduate level we do this, in fact in much more details also. Details of the design, different components, also more components, and also the drawing part also, that sketches, then illustrative sketches, all in more details also. But here we cannot take up or the details in the discussion because of the time constraints also, and it is not required in undergraduate level also. Okay. Now a water treatment plant is to be designed to process 50 MLD, which is equivalent to 50 into 10 to the power 3 meter cube per day of water. Jar test and pilot plant analysis. Jar test we already have discussed in my earlier this lecture session. Indicate that an alum dosage of this 40 milligram per liter. Jar test, I have described that, and in IS code also you will see the jar test details of this. Actually, based on that, the jar test, this test and the pilot plant studies, as it is given here, 40 milligram per liter of alum happens to be the optimum dosage of alum, and with flocculation at a GT value. This GT value already we have discussed in our previous lecture session, value of this, and for alum it is given this 4 to 6 into 10 to the power 4 or so, produces optimum results at the expected minimum temperature of 50 degrees centigrade. Minimum temperature also I told that we should work with the minimum temperature, we should design with the minimum temperature, that because that gives the maximum value of viscosity. As you know, the temperature when it decreases, the viscosity or density increases also. So that is why we have to take the minimum temperature that already has been discussed. Determine the monthly alum requirement as monthly alum requirement. Why? Because many a time we actually should have a stock for 1 month or so. So that is why the alum actually, the stock period, we consider that 30 days or 1 month or so, so that there is no scarcity of alum in processing of water also, so that consistently the alum is available to the water treatment plant operators or so. Second is that the flocculation basin dimensions, if 3 cross flow horizontal paddles, this is like that. That is why I have drawn this, so that you can understand immediately, you can connect this with this, right? Horizontal paddles, 3 cross flow. That means the flow is taking place this way, right? And the cross flow means it is perpendicular to the flow. That is why this is cross flow. The flow is taking place, suppose from here to there, right? And this actually is moving like that. Suppose if I take a duster like that, suppose this is a duster, so the plan or this actually, you will view like that, this is a sort of rectangular which I have drawn here. So these actually, say 4 dusters are kept like that. So this is moving like that, okay? Another duster is here. So 4, in 2 arms, 4 such these paddles are there. These are paddles, say. So this will be moving like that, okay? So that is why we are saying that, because the flow is taking place this way, and the paddle movement, these are in the this plane also. So that is why this is cross flow. Here, this is a continuation of this. Are to be used, the basin shall be a maximum of 12 meter wide and 5 meter deep in order to connect properly or appropriately with the settling basin. Here, as we have drawn here, the depth of the settling basin is here, is shown in the drawing or the diagram also, little below, because actually speaking, the settling tank, if the depth is more, then it would be extending below this one. This is the floor of the flocculation basin, while the floor of this one, it could be in the same level also, depending on the requirements of the settling basin also, right? And the width of the settling basin, that would be same as this, because see that in the settling basin, actually the water after flocculation, that flocculated water which has been flocculated or is being flocculated in this chamber after following the rapid mixing unit here, right? So this is the preceding unit, the rapid mixing unit, and this is the flocculation unit, and immediately following that one, this is the settling basin, and this settling basin has got common wall with the flocculation basin, so that the width, if it is remaining same also, then suppose this is the, I'm just trying to draw this one here, the plan. So this is the, suppose the flocculation basin, and here this is the settling basin, so common wall, right? The width may be different, that is the width and length is may be different. This may have a sort of longer or larger length also, right? This, but this actually common wall, as you see here, so that makes here the water through perforations, as I have drawn. So on the wall, common wall, the perforations are there, orifices, right? So it is going like that. So this will be moving from the flocculation basin to the settling basin, so that a very quiet and very quiescent condition, the settling takes place. So that settling, actually in settling tank, the flocculated water should not be disturbed much, right? So that otherwise what would happen, that if it is turbulence is created also here. Suppose if you give say it is like that. That means the width of the settling basin, it is plan, so width of the settling basin is more than that. That means here the turbulence will be there, because from this width, these are meeting with a greater width also, turbulence will be there. Same way, similarly, if it is less than that, then also turbulence will be there, because it will be going like that. So these turbulence, to avoid actually the width of this flocculation basin and the settling basin should be, it is a sort of recommended, it is recommended that it will be both the width will be same also, so that very quietly and in quiescent condition also it moves on to the next settling tank also. So that is why this is given. Now the third, this one is the power requirement, right? We have to find out the power requirement and the paddle configurations also. Here actually you have to understand this, that the design actually, the detailing is done so that you have got or developed an idea about the paddle configuration, how the paddles are placed, right, and the dimension of that and the configuration of that. So these are clear, so that is why I have drawn this one. I will further draw to clarify it further also, right? So here you see that this is given like that. So this is the 15 meter is the length. If you ask me that how we get, I am coming to the calculations. So based on calculations, it has been taken as 15 meter length, and the depth is 5 meter as it is written also here. This is this one, right? And 12 meter is this way, the width, which is equal to the width of the settling basin following that flocculation basin. So this is 12 means, as you see here, 0.4, 2.5, 2.5, 2.5, so 7.5, right? And this is 7.5, how can it be 12? Just 1 minute. 12, 12, 12, 1 minute. I might have made a mistake or so. Yeah. So this is, no, this is actually to fit into that, this should be 10.3 or so. Okay, I am coming to this later, why it is 10.3. Okay, so this would be 10.3, depth is 4.2, this is the 4.2, and then point this 4.2, 0.4, and this side also 0.4 also. So this will give that 5. This is 4.2, then this is 0.4, 0.4, 0.8, and plus this will be 5. So 5 meter depth, this one. And 12 meter maximum, it is written, just please note it, that here it is written the basin shall be a maximum of 12 meter wide. So it must not be more than that. So as per calculations, which we are coming later, we will see the width is becoming 10.3 or so, because this is 7.5, then it is 1, so 9.5, and this is 0.4, so this will be 10.3 or so. 10.3 will be the width. This is the width. This is the plan, remember. This is plan as written. This is the longitudinal section profile also. Okay. Now let me erase this just to create space. Now this example I have chosen to discuss here, because it more or less allows you to develop an idea about the problem, this solution, the design of flocculation system also. Now here you see that monthly alum requirement, the first one is very straightforward, very simple, right? So this is just 40 milligram per liter dosage, right? And it is processing 50 meter cube per day of this one, say suppose 40 milligram per liter of alum. Per liter of water you are using 40 milligram of alum. Okay, Now we could also write this as gram per meter cube. Same, because liter if you multiply by 10 to the power 3, it will be meter cube, and milligram if you multiply by 10 to the power 3, this will be gram. So many a time we, instead of writing mg per liter, we write straight away the grams per meter cube also. Okay, so this would be, you know, that 40, so this is kg, so this is this 1 kg into 50,000 meter cube per day into 30 days a month, right? So monthly requirements will be straight away, this will be 60,000 kg per month. Okay, so this is very straightforward, just one step calculations, but that actually will allow, or will you know, I mean will permit the engineers as well as operators operating the plant, they can have a 1 month stock of alarm, so that say today, from today, when you are operating, you have start operating this one, so that 1 month I mean ahead or later you can operate the plant without any, I mean, alarm shortage also. Then second thing is that, this one is the basin dimension. Basin dimension. So this would be basin dimensions. Now see here, step A, say. So assume an average G value of 30-second inverse. Okay, 30-second inverse. Now here one thing to note, that is, see that 40, this would be the 40-second inverse here, this would be 30-second inverse. Tapered flocculation we have discussed in my last lecture. I have discussed that tapered flocculation to save energy as well as to enhance the efficiency. Tapered flocculation is always, I mean, recommended also. So here also it has been followed like that. So first compartment, actually this is the, you know that, I mean, perforated, this is separated by this one. Sometimes it may not be separated, just the virtual kind of separation that will be there. But many a time perforations also are there. So there actually you see that average G value that becomes 40, 30, 20, so average is 30 second. Okay, so if we take that average, based on which we will calculate the volume later, so GT, that is 4 this, then T is equal to, if we put 30-second inverse, so this would be 4 into 10 to the power 4. This is, remember, dimensionless, because the G that actually per second and T in second, so that is why this product is dimensionless, remember this. Okay, so this divided by 30, so this would be in minute, if you convert this into minute or so, so this would be, say, 1 minute 30 second, so that is 60 second in 1 minute. So this actually will give you T value 22.22 minute. Okay, so this would be the detention period of the water flow in flocculation basin also. So the volume of the tank will be, so the volume B, liquid volume of course, that is the liquid or wet volume, liquid volume of the tank. So that will be V is equal to Q design into detention period. So Q design is stated 50,000 meter cube per day into that 22.22 minute divided by that is 1440, that is 60 into 24. So 60 into 24 minute is in day also. Okay. If we write like that, always try to write like that. That means this much minute makes a day, or one day is equivalent to 60 into 24 minutes. Then your dimension analysis and dimensioning, that actually will be more or less, I should not say, it will be correct also. Otherwise it may you may mistake also, you may commit some mistakes in that dimensioning also. So that is why it is always better to write like that. So this would be 7, the value, as I am following this PV row book where the values are given, so that is why I am using the value. You can check, verify these values. Okay. Yeah, if there is any discrepancy also, then try to correct yourself, or we can discuss this when we will have regular discussion in weekly discussion or so during the course also, right? So there we will have the opportunity to discuss it further. Now this actually, you see that this is the volume. Okay. Now the tank will contain 3 cross flow these paddles. So its length will be divided into 3 compartments. 3 compartments we have shown. For equal distribution of velocity gradient, the end area of each compartment should be a square. That is, the depth is equal to the length. That means, just let me explain this further. So this is the, I think you have understood this. If there is any doubt or sort of clarification needed in understanding this, then you can get back. We can discuss this further later. Okay. So what we are there, you can see it is a square kind of this one. That means this is this, if you see, squarish in the sense that the depth, this is the length, total length, right, 15 meters. So each is having 5 meters, say 5 meter, 5 meter, 5 meter. So that way, square means this way, if you see. So depth also is 5 meter, as I have told that this would be the 4.2, then 0.4, this 0.4, this is the depth, say. So this would be the 5 meter also. This is this side 0.4, this side 0.4. So this makes this 5 meter. So 5 meter, 5 meter. That would be that. That is the depth of in each chamber. The depth of liquid. This is 1/3 of the length also. Assuming minimum depth of 5 meter, length will be, so 5 meter depth. This depth actually. So this would be, sorry, 5 meter will be here, not here, up to the liquid level, from bottom to the liquid level also. 5 meter into 3 times, so your L will be 15 meter. Okay, so we have taken the length as 15 meter or so. Assuming that we are providing a square kind of in section, this will look like a square also, 5 meter by 5 meter. Right, here also 5 meter by 5 meter, 5 meter by 5 meter, so that a sort of uniform motion, so that is there, and one paddle in each, this one paddle or one sort of shaft with 4 paddles, say in 2 arms or so, right? These are arms on which the paddles are 4 paddles on each arm. 2 paddles are mounted, here 1 and here 2 and here 2, 4 paddles. Okay, so this would be 15 meter or so. So width will be, our volume was this is you know that width will be 771.5 meter cube, that is the volume, divided by 15, that is the meter length, into 5 meter is the let us say the depth, or so D, right? So this would be the volume. So this would be giving you 10.3 meter. So this width actually will be 10.3. This side will be, this will be 10 meter, and this width we have shown here in details. See, so this will be 10.3 from here to here. This would be 10.3. If you see this one, I think I have not written anywhere, but here let me write this. This 10.3. This is the width, right? And how it comes? That is 2.5, 2.5, 2.5. So 7.5. The here the division, that the wall, partition wall also. So that is actually 1 meter, 1 meter, and then this is 0.4. So 1, 1, 2, 9.5, 9.9, and plus 0.4 this side. So 10.3. 10.3 will be the width. And see that here the shaft. Here you have to understand this shaft. Now this is actually. So this is, if I draw like this, that is see, that would be yes, with respect to this drawing only we are drawing this one, okay, or different color we may prefer, okay. So this is so these are the paddles dimension here. So this is rotating like that, right? So this would be rotating like this. This would be rotating like that. And please note that here this arm on two sides of the shaft in the same plane, vertical say here, this is connected like that. And the paddles this way here, this will face it like that, and this will face. That means when it will be coming like that. So this would be, if the duster suppose is that, so right, or this is like that. So this will be moving like that, okay. And you see that here this is going like that. So on the opposite face also that will be there. Now this would be see that here this is the width of the paddle. So this is suppose W, not this width. This is the paddle width, okay. And if we see this here, here you have to understand this. First thing is that because if you do not understand this, then it is difficult for you to sort of, solve the problem in the examination or in competitive test also. Here you see that this is the pedal, right? So this is the pedal. Like that, okay. So this one pedal, it is 2.5. So it is extending this way 2.5 meter, which is that here, let me write that 2.5 meter. Same here. Similarly for this also, this should be like that. So this pedal is rotating like that. Is why I have tried to show the duster wise, because the duster, as you see here, the duster has got a 2.5 meter length here, right? And this is the width we have to find out later. Okay, so that is why it is looking like that, as you see here. This is looking like this, right? But actually speaking, this is like that. So when the pedal is moving, so it is moving like that. So that you are seeing this part, and the pedal that side, from this side you will see like that, okay, the pedal. So that would be there. Now you see that, okay. So this is the configuration. See, the shaft is at the middle of the, more or less middle of the each chamber also. This is the compartment, say 3 compartment. Right? So 3 compartment here, middle of this actually the shaft is mounted also. So this is the shaft, it is embedded in the wall so that it could with bearing. So there is a bearing also. So this will be moving like that. Okay. So this is here, it will be moving like that. Okay. This will be moving like that, or it is something like that. Say here, this will be moving like that. The shaft extends this way, perpendicular to the board. So this will move like that, and this actually, as it is that the blades or the pedals are mounted, right, through arms or so. So this also will be moving like that when we are moving this way. I think I could make it clear. But if still clarifications are there, then I would sort of advise all of you to discuss this or interact later. Okay. Now this is the configuration. With these configurations, and these are the compartment, this compartment having perforated wall or imaginary this one. Sometimes from here it is moving on to the second, then on to the third chamber or so, right? And shaft is at the middle. So this is the chamber, right? One compartment, and middle of that, this is another compartment, middle of that shaft is mounted. Here also shaft is mounted. So 3 shafts are there, separate shafts. Now third, this one component of that, this is the that third one, that is the power requirement. So pedal configurations, as I have discussed as much in details as possible also. So I think you have got it. So this is actually assume G value, that is there taken, or that this first compartment G 42nd inverse, as we have already written, right? So this is the tapered flocculation also. So that is already discussed. Now here the first one is that in the first compartment the power, this one is a P say 1 first power for this, that is mu V G square. This is already equation, already we have used in my last this one for rapid mixing unit design also we have used the same equation also, right? So P1 means the power for the first compartment, power to be, power to be transmitted also. This is same because the same water is moving from one chamber to another chamber. V is also same because same configuration, square in section, as you see, and G1 that differs. So G1 is equal to here 40 second inverse, right? So this is we have 40 second inverse. So this is actually, see that I think that we have, just one moment, yeah, 40, you can just note it, that V is equal to this. So 40 first compartment, 40 this one. We I think earlier we told this would be 40, right? Because I wrote it, but now it is earlier one has come, 40, then 30 second inverse, and this is 40, 30 and 20 second inverse. That is, I just discussed just short while ago, but here earlier one was there, I think that is why this is. So 40 second inverse for that G, and the mu value at 15 degrees centigrade, 1 point from literature you will get this. That is Newton second per meter square. That is the mu value, right? So P1, if you calculate, then this would be, and the volume will be, you see that 771, right, total volume. So for each compartment the liquid volume will be this divided by 3. So this is the, say, volume. V1 is equal to V2 is equal to V3 is equal to Vy3. This is equal to 771.5 by 3, that would be 257. You can check this value. Okay, so this would be this. So your P value, this would be mu V, so 1.139 into 10 to the power. For one compartment I am doing the detailed calculation, but for the later one you can do yourself. Okay, only the value you can check. I may put the values so you can check this. So this mu V, so this would be 257.2 meter cube. This is P is equal to mu, that is Newton second per meter square, into G square, that is 40 second inverse. So this is square, right? So this would be, I think I am correct, this one. This is mu, this is V1, and this is G1, so G1 square. So this is G1. Okay, so this will be 468.7 Newton meter per second or watt. So this will be 0.47 kilowatt, because this will be in wattage, this is watt. So divided by 10 to the power 3 gives you the, in kilowatt, what is the power for P1 for the first compartment. So second compartment, similarly you can calculate, this is 0.26 kilowatt, and third compartment P3 is 0.12 kilowatt. These values you can check. Okay, this is already calculated. So P2 and P3 you can check these values. Okay, I have given here the straight this, I mean from the book also. Okay, so I think it is clear to the viewers that how it is calculated. First we have calculated the volume, considering the depth and the length of each compartment. 3 compartments are there, and the length of each compartment will be same, right? So there is no variation here. So all will have same length of say 5 meter, 5 meter, 5 meter. We have configured like that. Okay, and depth also will be 5 meter liquid depth from the bottom, because some allowance will be here, otherwise it will touch the bottom, which is not desirable at all. And here also with respect to liquid level also, suppose the liquid level is here, so this should be little below the liquid level also, right? It should not be above liquid or very on the surface also, it should not terminate. Okay, so this actually we have calculated from the detention period. Detention period is calculated from the GT value, given GT value 4 into 10 to the power minus 4, 4 into 10 to the power 4, that dimensionless figure GT, from which we have found out that T, total T and total volume. Then for each one of that the volume will be 1/3 of that. So we have calculated this V1, V2, that these calculations, and power we have calculated. Okay, now pedal configurations wise, see the pedal configurations. Pedal configuration. Each pedal wheel has 4 blades as shown here. So this would be that 2.5 meter long, as we have shown this way, and 2.5 meter we have configured like that. This is 2.5 meter, 2.5 meter, 2.5 meter. Okay, so that is how it is taken. Now long and width, actually the width, omega width also, pedal, this one width, 3 pedal wheel, that compartment that is there. So calculate omega, or say this width. Let us not get confused with this width. This is the chamber or the flocculation basin's width, not with the pedal width also. Pedal width is, that is why I am writing the small w also. Okay, whereas this was capital W if you write like that. So this would be that power input we have already calculated. So there is another formula which I have explained earlier in my previous sessions. This is this rho and VP cube. Actually VR, this is VR. So BP we will calculate, but at 15 degrees centigrade, rho is 999, little short of this 1000 kg per meter cube. From literature you get this one. So assume that VP is 0.67 times into 0.75, that is say 0.5 meter per second, and CD, okay. Now here one thing you have to see, that how we have taken this one, that is from the you can, if you go back to my earlier lecture, this notes also, so there you will find that this actually there is a range. So we have taken that 0.75 we have kept 0.67 meter per second, and 75% of that as VR also. Let us say VR, not VP. VP is the peripheral velocity. So that actually 0.67 is that peripheral velocity, that is assumed or taken from the recommended range also, and 0.75 times means 75% of that peripheral velocity, that happens to be the VR, that is the relative velocity, what we have already discussed. So this actually, you know that AP is length of boards into this, into number of boards, right? So we have got 3 panels, as you see, 3 panels at 4 boards, 1, 2, 3, 4. Let us say that 4 boards or panel, wooden panel also, per panel. So 12 this, you know, boards are there, right? So three panels. No, this actually I have made a mistake here. Let me tell you that this 3 panels means here, this 3. One segment here, another segment here, another segment is here. And there, as it is, if it is given the entire this one sort of, I mean, the wooden or the board also, then it will be sagging also. So that is why actually what way we have given, that is this way, here say 1, here another, here another. So this will have separate, you know, connected, because one shaft is there, but separate segments are there, so that by the weight of that, it does not, you know, I mean, get, you know, I mean, sagged also. So that is why we have taken the 4 boards, remember that, 4 boards, then 3 paddles in one sort of this one, this way, 3 paddles we have sprayed, that is 10.3. We have taken 3 this different kind of diameter. One this, let me sort of draw it more clearly so that you can understand it. So I am here a little bit extending this one here, right? So this is another, say, this is another. So total is 10.3 vertically, this way, the width, along the width. So 10.3, 2.5, 2.5, 2.5 as here given, okay, to clarify it further. Now, so your paddle area AP will be 12, that is a 12 means here 12 boards will be there, number of boards, that is the 12, that is 4, next segment 4, next segment 4. So 12, and omega is to be calculated, and 2.5 meter is the length of each. So this would be 12 into 2.5 meter into omega, that is in meter also. So that is equal to 30 omega, that will be your AP. AP means for first compartment, what is the total paddle area? That means this paddle area, 3. And this is in series this way. Okay, so 30 W or so, that would be, in terms of W, we have to calculate this W. So that way you can, I think you can, you understand this. Now here one thing I should say, that we have assumed a velocity of this. What you could have done, that is the width of the paddles, or sorry, the depth of paddle, let us say the depth of the paddle, that actually you could have taken from the standard dimensions of that. Suppose this is a dimension has got, right, this the depth. So this depth you could have taken, and you could have calculated that this VP and check that VP. But what we here it is done, that from the range the VP is taken, that is a peripheral or tangential velocity or so. Then VR we have calculated 70 to 80%, so we have taken 75%, and we have calculated VR also. And then we have put this VR value and found out that what would be the omega or the depth of the paddle also. So here width of the paddle we are saying, but better to say depth, because this is the depth actually, and this is the you can say length of the board also, as we have written. Okay. Now this will be, so P1 already calculated 468. Here we are writing in wattage, because ultimately this has to be in wattage, the consistent this equation also. So this would be, you see that, so half CD is 1.8 into 30 W, that is AP. We have an AP, then 991.1 kg per meter cube, and VRQ, that is 0.5 meter per second, that is cube. Okay. That means we have applied this equation. This is another equations I have already discussed earlier, that power which will be transmitted also, that depends on that power, how do you consume, that depends on the paddle area, then relative velocity and density of water, and that configuration of the paddle, that CD for flat blade, Newton's drag coefficient taking as this one. So we can calculate. See, there also this is another formula. P you have calculated earlier, mu Vg square. From that P is to be consumed by having these configurations and the dimensions of the paddles also this way. So ultimately that will be giving you the, that is the omega or depth of that 0.14 meter. Okay. Now this would be Vp, if we go like that, pi d into omega. So this actually you can find out that 4.2, right, that d diameter of that is this 4.2, this one, di is equal to this, but here we are taking that end, the tip velocity here. So accordingly pi d omega, this is the d, this is the center to center distance of the impeller, but actual diameter of this one is d. So pi d omega. So Vp will be, you know that Vp is given, so this would be say 0.67 meter per second. So from which you can get, this one will be the omega, that is the revolution. Okay, this the revolution or RPM also, that will be 3.05 revolution per minute. Vp we have taken here. Please note that we should not get confused, because same notations we have used. So I think it is better to use n, that is the rotational speed, this rotational speed. Okay, so let us say n instead of omega. Although I have earlier also told that this many times omega is represents the angular rotation also, but here we will prefer to use n, because already we have defined like that. If we would have written say this as d, that is the depth of the paddle also, then we could have written omega also. But as we have written here w, let me not change that one, n we will use. So this actually will be n, so n will be this. So that will be the rotational speed for the first rotational speed of the shaft, right? The shaft is rotating like that, shaft is rotating. Okay, so this shaft rotation is n is equal to 3.05 RPM or so. And as per this one, I think you have taken a note of that peripheral speed is 0.15 to 0.6, that was there, right? And you can see that RPM 1 to 3 RPM, that is usually it is the recommended range is the 1 to 3 RPM or so. So it is more or less, 3 RPM, not very, much more than 3. So it is acceptable. If it is say within 5% or so, it is acceptable also. And similarly, so the second, this compartment, this is for the first, second compartment I am giving directly the value so that you can check this. Okay. So second compartment and third compartment also, same or similar calculations will be there with different values also, particularly for G also, this value. So this would be for this one, omega or N2 say. This is N2. This is N1. This is N3. This would be different because the G, what you have to create by rotational speed also, that and pedal dimensions will be same for all three. So only this, actually by changing this one, by reducing this one, you can reduce G value also. So here this would be, let us say that N1 for first compartment, for second compartment this would be 2.5 RPM, revolution per minute, and third compartment, that is N3, that will be equal to third compartment 1.91. So N1 if you write, then 3.05 RPM. So this is very close to 1 to 3 RPM, which is the recommended range also, right? So that design is here up to this. So you have to understand that how do you configure this one. This is very important to understand, and when you will be an experienced designer or so, then you can you can sort of choose the dimensions according to your experience as well as consulting with the manufacturer. So at every stage a designer should be in close touch with the manufacturer or suppliers also, because the availability in market, so that must be guided by the manufacturer also, and you have to just simply this one, you cannot that fabricate, then it will be delayed also if you fabricate or customize the configuration also. So that is why better to use the standard this boards or the pedals also, and here shaft speed you have to calculate also, and the dimensioning you have to do according to the detention or according to the design values also, and the perforation size also. I am not detailing this one because at this stage you don't require this one, the perforations, what would be the perforation size also, because these are in the more detailing of the flocculation basin also. So we should stop here, we should conclude here, and hope with a hope that you have more or less got an idea, and if you want to sort of develop a better idea, more thorough understanding also regarding that, then we can have a discussion, as I have already intimated, that we will have 2 Google Meet per week, 2 Google Meet of half an hour duration. Google Meet means virtual meet also, and where you can throw questions also, and we can interact, right? So that you develop your own understanding, and that based on very thorough interactions, you can clarify your doubts also in that Google Meet sessions also. So with this, thank you so much. Okay.